All right, so we're right at time. Good morning, good afternoon, everybody in the Americas. Good evening in Europe and Africa. And maybe again, good morning in the far east of Asia and Australia. So welcome, everybody. Thanks for joining this session. My name is Olaf Weber. I'm the CTO of Hansadrone. And my topic for today is how to use the MAVSDK and Offboard mode for precision approach without having a camera on the drone. Okay, I need this window. Yeah, my talk is about like 30 minutes or so today. So I would propose that I just finish my slides. That will take like 20 minutes, and then we have time for questions and answers. As always, if you already have any questions, put them to the Q&A section so we can walk through that afterwards. In my talk today, I would like to take you with me on a little journey to the future, a hopefully not so distant future where drone delivery has become a reality. And we all know we're not too far away from that. So there has been tremendous improvement in the drone industry in the recent years. We see the Autopilot becoming really mature with PX4, of course, leading the pack. And we see drones becoming very reliable. And also we see integration, software integration of drones into the airspace management becoming more and more available. And of course, also we see the airspace authorities around the world are working to get drone delivery, autonomous delivery become a reality. This is the FAA, of course, working on that in the United States, but also the EASA here in Europe. But let's stop for a minute and go back to today. So global package delivery is skyrocketing. Yeah, we see the number of packages is increasing by 2-digit numbers year over year, just doubling within just a couple of years. And this is all driven by global megatrends like urbanization, like e-commerce, of course, like people moving to single households. So people like to order things online, be it grocery shopping, be it e-commerce, be it food delivery. All this stuff gets delivered to customers' homes. And of course, the global pandemic has even further driven this trend. People stay more at home, work from home, and order things online. This is causing all kinds of problems. So we see delivery vans blocking the streets. We see package waste, tons of package waste piling up. We see that delivery companies even have problems finding enough workforce to fill the demand. And still, we see that customers ask for ever faster and ever cheaper deliveries. Drones, of course, have been proposed to solve that solution. A drone could deliver almost any item that's not too bulky or too heavy to a customer. So be it like grocery or be it food or be it urgent medical deliveries, a drone could bring all that right to your place. And of course, this is not new. Yeah, we see a couple of companies performing deliveries and test cases around the world for a couple of years now. You see here in our Google Ring, but there's more companies also performing that. And of course, we all agree, wouldn't it be so convenient to get your deliveries right in your backyard? But what if, and that's my problem statement for today's call, what if you don't have a backyard? What if you live in an apartment? And that's actually the case for many people. In many countries around the world, we see that a majority of people is living in apartments, be it along the US East Coast, be it in Europe with its old city centers, or be it in Asia or the Middle East with its hyper-modern cities. In all those places, the majority of people lives in apartments. So how could a drone serve those people? And we believe in order to make drone delivery really available to the mass market, you need to serve urban, densely populated areas as well. So the question is what to do. Yeah? How could a drone actually make a delivery to an apartment? How would a drone find me if I live in an apartment, which I do actually? And how could it serve me and where would it land? And it starts with a very basic and simple question, and this might really sound stupid here. The question is, where am I? So to tell the drone to bring something to me, I need to tell the drone, where am I? And of course, I have a street address and I have a house number, but this is not helping here. Yeah? The entire building has the same address. So this is not working. And of course, I know what floor I live in and which apartment number, but again, this is not working because this is not known to the drone. So pretty straightforward, you would say, well, you have a smartphone, you can use your GPS signal, right? And yes, of course, this could be done. But the problem is that the GPS usually has an accuracy of like plus minus 5 meters or so. And in case of an apartment, this already means that the drone could deliver like 2 floors above me or below me, or could fly to the apartment next door. So this is not really working. And even worse, in many cases, I don't have a GPS signal because I'm based indoors and there's no satellite coverage. So I would need to fall back on a cell-based navigation, which works actually pretty well in cities, but still it only has an accuracy of, let's say, plus minus 20 meters or so. So again, this would not be suitable to tell the drone where I am. Of course, a solution that had been proposed many times is to have some kind of marker on my docking station on my balcony, and then let the drone find me by putting a camera towards my place and then figure out where I am. But to be honest, is that really suitable in this case? So if everybody had a docking station on his balcony, first of all, that's expensive, first of all, or second, who's mounting that, who's maintaining that? And then do we want to have the full building covered with markers? This is not really suitable. So what works fine for as a research project might become a problem in reality. And it doesn't stop there. So the question is, if the drone really wants to find me by using a camera, it has to point a camera right into my bedroom and my living room, and not just but also the bedroom of my neighbor. And this might really cause privacy issues. And we believe privacy is a key concern. To really have broad acceptance across the users for drone deliveries, we need to address those privacy concerns. So really facing a camera towards the customer is not a solution. And even if you say we're using that signal only on board, you know, people, they never trust you. So the easiest way would be just not to have a camera at all. So here's a solution that we came up with. So if we can't have a camera on the drone, and if we can't have a marker on the balcony, why don't we just turn things around? So we can easily install an app on the smartphone and then use the smartphone camera to recognize the drone. And this is actually an easy one. So just pointing my camera to the sky will not cause any privacy issues, and it will easily recognize a drone against the sky. And on the other hand, we can easily put a marker on the drone. So that would just be a light, a bright light. And for example, the landing light, which is a mandatory thing for drone to have. So I could use my smartphone to recognize the drone. And we instantly recognized, okay, there is more to it. So if we're now using a smartphone app to recognize the drone, the smartphone also has sensors for the magnetic field. So like it's a compass actually, and a gravity sensor. So I can figure out the inclination vector. So I could use my smartphone to define a direction from where the drone could approach me. And this has a number of advantages. So the drone would not have to hover above my place and find a way towards me, but I can directly tell the drone from where to approach me. And this would reduce the time that the drone spends in lower airspace, so it can fly in and fly out very fast, reducing noise, reducing any annoying parts to my neighbors. And even more, we recognized, okay, so now we're using the camera to recognize the drone. We can use the same camera to recognize free sky. So we have trained an AI model with thousands of images of obstacles and free sky, and trained then Google Cloud Vision TensorFlow Lite model that we can integrate to the app. So this AI model is used for real-time image recognition of free sky. And it recognizes any obstacle, be it a building or tree or power line or any other flying drone. And it would only allow the user to define a direction if the sky is really free of obstacles. So putting it all together, we have actually just defined a spatially stable 3D object which can be used as a safe approach corridor for the drone to fly from its cruising altitude towards me as a customer in my place. And this corridor looks a bit like a pyramid with the pointy end on my end, yeah, with the camera, and the base facing upwards in the sky. And this corridor is defined by the GPS position, as mentioned before, by the inclination angle, by the compass angle, and of course by the camera opening angle. And also we have the corridor image that we just took to validate this corridor is free. Now this corridor is like a 3D object that can be used for further validation. And we can match that data with 3D data, like for example, here we have OpenStreetMap building data, which is available for most cities around the globe in 3D. So we can see, is that corridor somehow interacting with buildings, or is it interacting with no-flight zones, like what you see here on the right hand, the red area. And only if everything is clear and free, so AI image recognition says okay, and all the intersecting with the 3D data says okay, and only then we could define the safe approach corridor. So this is the way actually for the drone to fly from cruising altitude towards the customer. And the drone would now fly to a fixed point in the sky, which is like the intersection of that approach corridor with the cruising altitude, and it would start its approach flight from that fixed point. And we just learned our GPS signal is not really reliable. Yeah? It might be a couple of meters off, and actually the same is true for the compass. So compass signal could easily be deviated. If I have some metal in my window frame, for example, then my compass is a couple of degrees off to one direction. Or I don't have even a GPS signal. I might have to rely on a cell-based signal, which is 20 meters off or maybe even more. But the good thing is with our corridor, we define a very wide window. So at cruising altitude of the drone, that window is easily like 200 meters wide. And if we have a deviation of 20 meters or even more, or a couple of degrees, our defined fixed point would still be inside the corridor. And the drone would still be recognized by the smartphone app. So let's assume the drone has arrived at our fixed point. So towards that point, of course, the drone will fly using some flight management system. It will be integrated into the airspace. All this is up and under development and coming one day, hopefully. And now the drone is at the fixed point, and the customer will point his smartphone again towards the defined direction. And it's actually like an augmented reality. So the corridor is stable as soon as it is defined. And then even if I move my smartphone, I see that corridor inside my smartphone moving. So I point my smartphone at the same direction and recognize the drone. And now I could use that information actually to provide guidance to the drone. So I could tell the drone, hey, you're a bit off to the left, or you're a bit high or low. Please correct your position. And the drone could use that information while it approaches me to iterate through the corridor, always correcting its position, narrowing down until in the end, the drone would hover just in front of my smartphone camera. And this works actually pretty well. So in the end, this has an accuracy of like 10, 20 centimeters, where the drone could start hovering in front of me. Stop hovering. Yeah, you might have noticed we're using this special design of a drone. And this is actually a drone that we have built. So we're not a hardware company, we're a software company. But still, we have designed this drone prototype to showcase the end-to-end solution, how that could work. And the unique thing about this drone is it has ducted rotors. So that's, of course, necessary for the drone to approach the customer, to not cause any danger here. And it has ducts and it has a mesh. So that's like a tennis racket. So you cannot stick your fingers in there. It's quite solid, actually. And also the drone has a large body, which is shaped like an airfoil. So it produces some extra lift during use flight, but it also provides room for the package. And yeah, then it has handles in the front and the light. And it also has an ultrasonic distance sensor, and we'll come to that later. So let's have a look on how we have implemented this solution. First thing is we have a mobile app, and on this mobile app we have the trained AI model, which is a TensorFloat Lite model. And the app, of course, is connecting to all the system services like the camera, the compass, GPS, and so on, to define the safe corridor and to store that data. And then the app is connecting to a cloud-based backend where all the data is stored. So for example, we have also the image, the free image stored there, and we have also a video from the approach flight stored on the server. So in case something goes wrong, you can always look that up later on. And we can, of course, also use the data on the cloud to interact with further external data providers like OpenStreetMap, like no-fly zones, whatever. And from the other end, we have a Python script that uses MAVSDK to convert those data from the cloud to MAVLink commands. So the Python script is loading the fixed point data, is loading the corridor data, converts that into set point data that can be sent over to the drone. And then later on, when the drone is recognized again, the Python script loads the deviations from the server, converts deviations into offboard commands, and sends it to the drone. Last but not least, we have the drone itself, which is just a standard drone running standard Pixhawk 4 PX4 Autopilot. And this drone is, of course, recognized again by the smartphone camera. And this closes the loop. So it means we have like a closed control loop during the approach flight. Just a few lines of code, and I really don't want to bother you here with too much software source code. You can look at all that on our website. So first call is then here's the API call to our API where you download the deviations, and the deviations actually is an angle. So this is how the drone is recognized from the camera perspective, left or right of the center point of the corridor. And then we need to convert this into actual deviations. And for that, we need the distance of the drone towards the user, which is also not known in the beginning, but we can use the inclination angle and calculate the distance from that, because the inclination angle is based on gravity, and gravity is hard to fake. So gravity is quite reliable. So that means the inclination angle is also reliable. Yeah, but still converting the deviations into correction parameters is actually quite a tricky part, because we don't know where the deviations come from. So we have two examples here. On the left-hand side, you see that the compass is a bit off, and on the right-hand side, you see the GPS position is off. On the left-hand side, you see the customer is with C, pointing his smartphone towards the air, towards the sky, defining the corridor and defining a fixed point for the drone D to fly. This is in the blue system, but there is a deviation. The compass is actually wrong. So the real system, which is here in black, is a bit turned to the right. And the real center line of the corridor is actually the red line. So that means when now pointing my smartphone again, the drone will not appear in the center. It will appear to the left under an angle beta. And now the drone is recognized, and we can use that signal to calculate a new position for the drone. And for that, we take just a simple algorithm. We take half the deviation angle and then fly inwards on that angle and then forward a step. And the step length is actually just a percentage of the corridor distance. So that step length gets reduced the further the drone approaches. From that, we calculate a new drone position, which is D1, and the drone would now fly towards D1. And you see D1 is much closer to the center line of the corridor. So even overshooting a bit here, but still much closer. And then the drone will repeat this process over and over again, and then reducing the distance to the center line further and further until eventually the drone is just hovering in front of my camera. And the same works also if the GPS signal is off on the right-hand side. And in reality, you usually see a combination that both the compass and the GPS is off. And that might even be compensating itself, but still the drone is then showing up in the middle and then progressing and flying out of the middle again. This algorithm still works. Yeah, so then we have calculated our new approach set point. And now we use the offboard mode from MAVSDK to guide the drone by really telling, okay, go like 5 meters forward and 1 meter to the right. And there's two ways to do so. One is the northeast down position command, and one is the northeast down velocity. And we tried both, and with the northeast down position, this is for us a bit rocky. So the drone would accelerate quite hard and then stop hard, and which just doesn't look very nice. So we decided to use the velocity command. Means we break down the new set point into northeast down velocity subparts and then set a low speed, like 1 meter per second or so. Again, breaks that down by the components and then lets the drone fly very smoothly towards the customer. And of course, you can reduce or increase the speed as needed, so you can start fast and then slow down a bit more. Yeah, for the last meters, I already mentioned we need an ultrasonic sensor that we use to really get the drone in like in 10 or 20 centimeters accuracy. And this is also natively supported from MAVSDK. So from high-level components, you can directly call the sensor distance here and get the sensor distance into centimeters. And then for the final approach, you can even tell the customer to turn the smartphone away. And you have a final angle, you have a final distance. And from that, you can calculate the final approach. Eventually, your drone will start or stop, right in front of your balcony or window. And this is actually what this system allows. So you can make deliveries to places that could not be served before. Drones can fly towards windows or balconies and hand over delivery. Of course, the system is not limited to making deliveries. Yeah, it's a generic system that can be used for precision approach to any point where there is no landing location or where the point position itself is not known up front. This could be up in the mountains, for example, or this could be on board a ship. Wherever you need to bring a drone to somebody who has a smartphone with the app installed, you can actually use this mechanism to guide the drone really towards that user. All that is implemented as a SaaS solution, which is currently in MVP mode. And this is actually the first time I'm presenting this. So feel free to sign up. Feedback is very welcome and much appreciated. It's all free, of course. You get your API key. You can download the app. You can download the SDK version and try it out by yourself. So, and this is actually it from my end so far. Thank you very much for joining this session. I think we're pretty good on time. Yeah. And we have a couple of minutes left over for questions, if there are any. So, loading Q&A. No questions so far. Then I have a question for myself. Does that work at night as well? What's working at night? Yes, it does work at night as well. Smartphone cameras are so sensitive today that you just need to increase brightness a little bit. You get a little bit of noise, but you can still use that image to recognize building, trees, and any other obstacles. And to recognize the drone, of course, is very easy because of the light source, and then guide the drone. Yeah, looking to the chat again and to the QA. So Mohammed is asking a question. Can we use Bluetooth for further enhancement in position? Yeah, not really. I mean, Bluetooth does not really provide you a direction. Bluetooth is good for ranging. And if you have like two Bluetooth receivers, you can, via triangulation, perform some angular ranging as well. But from Bluetooth itself, you don't really get a distance. And the same is true for Wi-Fi and almost any other just the radio-based signal. Any more questions? Let me see if the chat has something. Yeah, one more question from Joshua. How does the algorithm perform if the poor or internet connection with the customer's phone, poor cell coverage, causing dropped frames or other video issues? We're not transferring video actually from the customer's phone. So we're recognizing the drone onboard the phone, and then we're sending just the deviation, which is just a set of adjacent set of 2 parameters. So we don't need high bandwidth video connection for that. But yes, you are right. From your smartphone, you need to have internet connection. But at home in a city, I mean, leaning out of your window, you usually have that. And then I have a question from Julian. Have you tried connecting to the phone directly via Wi-Fi? I assume it's a pain to connect properly, but would it reduce the latency? No, we haven't tried that, but like you said, so for the real customer, it's not an option for that. You have to enable Wi-Fi, you have to drop off from your home Wi-Fi if you're in, you have to pair with the drone. So for a mass market, this is not an option. And latency actually is not really a problem. So the drone is not moving that fast. So if you have like a couple of 100 milliseconds or even a second of latency is not really a problem from what we found out. Another question from Jeff. Any testing done in direct sunlight with a light at sunset? And that's a good question, actually. It is causing problems, yes. So for now, we're using a red light on the drone. And if there's direct sunlight or sunset sunlight, red, this is causing problems. So one idea that we came up is with using a coded light signal. So you could use your light like a Morse code or something, and to recognize that code sequence to identify the actual drone light, but this is still in development. Arian is asking, how does the drone know who I am? Well, the drone doesn't know, but your smartphone app for sure knows. So this function would be integrated into your whatever Amazon, DHL, UPS app. So they for sure know who you are. And they have your credit card and your address and everything. And they would let you know, okay, your package is ready for delivery, and then you define the corridor. And then Anonymous is asking, any plans to integrate iPhone LiDAR with the solution? Not really yet, no. I don't know if LiDAR is able to recognize a drone on a far distance. I don't know what's the range of that and what's the resolution over a long distance. And the second point, of course, is then LiDAR only points in one direction. Yeah? So you have that component in any case to use compass and inclination sensor to define the corridor direction. All right, let me just refresh one more time. Time for one more question. Mohammed asking again, how do you deal with different camera models on different phones? That's not a problem at all. So any smartphone today has a reasonably good camera that can be used for this. We've tried also with very cheap phones and old phones, like 5-year-old phones. It works without problems. And then last question from Shavit. This might be slightly deviating from the focus of the presentation, but I was curious about how the wind dynamics may affect a drone delivery near balconies. Is that a problem, a big concern? Yeah. Wind, of course, has an effect on drones, but this is then more on the drone hardware side, actually. So for our algorithm, this supports just the deviations, and then, of course, it's up to the drone on how to use that. All right, I think we have reached our time. Again, thank you very much for joining the sessions and for the good questions. And of course, I will be around in the networking areas if more questions. And once again, if you like to try it out, sign up and download all the components and leave us a feedback. Thank you very much, and bye-bye.